So today I wanted to talk about rotationally invariant systems. So we'll basically be in the next three lectures we'll be talking about Hamiltonians of how to solve rotationally invariant systems. Okay. So if you ignore spin, and we're going to ignore spin from for the time being. So the question is, what is the most general form of a rotationally invariant Hamiltonian? Okay, let's just say one particle Hamiltonian. Although we will be describing two particles.
Yeah,
sorry?
The momentum square by m.
So Hamiltonian is p squared by 2m, yeah, and?
Plus L
And the potential.
squared by 2I or something.
So, and we have to add a potential, right? So what can we assume about the potential?
Rotationally symmetric.
Okay, what does that mean for the potential's spatial dependence?
So something called azimuthal symmetry, like, if I rotate around the axis and it won't change the value.
Yeah, but I want it to be rotational invariant around all directions.
Oh, okay, then a spherically symmetric
Okay, so now in principle we will depend on X, Y, and Z.
So it'll only depend on R, like the
right. So for rotationally symmetric Hamiltonian, basically what we can do, it'll just depend on R. What is R? R is the modulus of the position vector, right? So for example, V of R can be a power series in in R, right? That is good. That is the most general. That could be the most general. So okay. So now let me just prove that. Okay. So to prove this, let's first write. If I have, say, if I have a position vector R under a rotation, what will happen is R will be replaced by a rotation matrix acting on R, right? And we know that the modulus of R squared, which is, of course, equal to the number R squared. So this is the vector. This is not a vector. This is going to be R acting on, okay, under this transformation, let's call this, say, R prime. So this is prime, this is prime. So this is going to be R times R squared, right? Is it clear what I've done here? I've just used this equation. Okay, now what is this? This is nothing but R transpose of R transpose R, right? In a matrix language. But because this is rotation, R transpose R is equal to 1, because we know that rotational matrices are orthogonal matrices. They are part of the group of 3 by 3 orthogonal matrices, okay? R transpose has to be equal to R inverse. You guys know about this, right? Does everyone know about this?
Not aware of SO3, but more or less
But you
I'm
know,
aware of that stuff. Yeah. Yeah, this
yeah,
one. Yeah. I know.
yeah, that's all I need. It's a transpose is equal to inverse. That's all I want to know, right? So this is basically, so that means that this is going to be equal to R squared, which is just R squared. So we have proved that under rotation, R prime is equal to R. Okay? Now, so that means that this thing is rotational invariant. But what about this thing? So let's look at P squared. P squared is minus H squared del squared, right? So what is del squared? Well, del squared in Cartesian coordinates is del by del Ri, del by del Ri, where Ri is say X, Y, and Z, okay? Right, you agree? Or maybe I should use X. R is having to, carry too much of a burden. So Xi, okay? So this is what the Laplacian is, right? You agree?
Yes, sir.
Okay. Now, well, yeah, I'm in a notational quandary. Let's just, because here, yeah, R was actually better, because you'll see soon why. Okay. Okay. So now if I did under rotation, my Ri changed to Rij, right? That means that del by del Ri, so these are constant matrices. What will happen is that this will become del by del R prime of I, but this is related to del Rj, del R prime of I, del Rj. Now, what is this? If I look at this equation, this is equals to Ri prime, right? I mean, from this equation, I can figure out what this transformation matrix is. What is it? It's just Rij del Rj, right? So del by del Ri prime is this thing. Therefore, the Laplacian in the new coordinate system, in the rotated coordinate system, let's call it prime, that is given by del Ri prime, del Ri prime, but each of these is given by this thing. So I have R I J R I K del Rj del Rk. So here there's a sum over I. So this equation is nothing but, and see that the sum is over the first indices of both things. So if we transform this into a matrix language, this will be R transpose of R. We're taking the jk component of this equation. Then del Rj del Rk. But according to the fact that this is an orthogonal, that R is an orthogonal matrix, means that this is nothing but the identity matrix, and we're taking the jk component of the identity matrix. And there is a sum over both j and k. And therefore, if I do one of the sums, I get del by del Rj, del by del Rj, which is the Laplacian in the old coordinate system. So we see that under rotation, the Laplacian operator remains unchanged, right? Is that clear?
Yes, sir.
Yeah. And therefore, our Hamiltonian, our Schrodinger equation, which is this thing, right? Sorry for that. Kali is very naughty. Let me just let him out. Okay, go on. As soon as I let him out, he wants to come back in. Okay, so this equation in our coordinate system in the position representation is minus h squared by 2m del squared acting on psi plus v. Now, this is dependent only on r because we're assuming spherical symmetry. And then I, h of psi, del psi of del t. And we see that this is a rotationally invariant equation, right? Now, how does psi transform under rotation? Psi basically should, because it's a scalar quantity, it should go to psi prime of, say, x. It should depend on the old psi by r inverse acting on x, okay?